Hi, and welcome to our lesson 8.2. Today we're going to be talking about looking at the population proportion, but from a differing perspective. We'll begin talking about hypothesis tests today. And to help us enter our discussion about hypothesis tests, I'd like you to think about this. A couple years ago, this was poor Linda. It was too hot to be outside last Monday in Zephyrhills, Florida. I spent the afternoon playing dice games, because my mom and I are we like to play board games, dice games. Notice that in one set of 40 rolls, I got 12 sixes. Now that seems like a lot to me. I mean, I know that 1/6 of the rolls should be sixes, and I wondered if that was like an unusual event. I didn't really wonder if the dice was fair, because I'm pretty sure my mom does not have loaded dice. But if you think about that, folks, in 40 rolls, I should have had 1/6 of them be sixes, and 40 over 6, 40 over 6 is around 6 2/3 or 6.7. I got definitely more sixes than that. What I'm wondering is that enough over what I would expect to make that be unusual? So obviously, I had more sixes than I would expect. Okay, there were more sixes than you would expect. The question is that an unusual event? I know it's different, but is it different enough to be considered statistically unusual? Okay, so you have, or we have, the capability of answering this question already. I mean, I have I'm going to call it this. I have p hat 12/40ths. That's from my sample, my 40 rolls. Q hat would be 28/40ths. If I perform my tests for criteria that we've used before, multiplying p hat times n would get me 12 successes. Obviously, I had 12 successes, which is bigger than 10. So we're okay to use statistical methods here. The rolls are independent, binomial. It's either a 6 or not. And the population of rolls is infinite. So our criteria are met. So let's just take a stab at this. How unusual is that? Let's figure a z for this. A z-score, as we know, takes the test statistic, which is 12/40ths. It subtracts the mean, or expected proportion in this case, which is 1/6. It divides by a standard error, okay, since we're looking at a sample of 40. The standard error, I'm going to base that on what's believed to be true. See, that's the rule we're operating under. So 1/6 times 5/6 all over 40. I'm going to go ahead and put that in my calculator, and I'm going to ask you to do that as well. You should. All right, as you can see from my calculator, I've done my z calculation. The z-score that I got is 2.26, and folks, the question is that unusual? Well, unusual depends on what you're comparing to. So I'm going to ask you to think about what we've done previously in our z comparisons. Likely values are, if we're talking about 95%, likely values are somewhere between negative 1.96 in the z and 1.96, and mine is definitely beyond that. I have more than 2 standard deviations above the mean. So yeah, this is unusual. Okay, now I don't know whether that means that dice was really fair or not, but I do know that it's outside the realm of what we'd consider usual. Okay, and that's exactly the kind of thing that you do, the kind of thinking that you do when you're performing a hypothesis test. Before we start our formal discussion, what we did really is an informal z-test there. I want us to think about this. What is considered critical? In the previous example, if we got behind or beyond 1.96s on either end, we considered that unusual. And again, you know that is the middle 95% of values inside. We've used that for quite a while. That means that on either side of this, there is 0.25 of probability left. And when you're doing hypothesis testing, Instead of calling it a 95% test, you call it a test at the, well, I'm going to add those two together. That's the 05 level. We tested at the 05 level. That is, things are considered unusual if they're in the outside 5%. Okay. All right, I want us to think about this a little bit more. We're going to add some information here before we talk about the formality of the test. Our test happened to be two-tailed. That is, we were looking at unusual events occurring at both ends of the spectrum. Now, the two normal values or levels of significance for testing are the 05 level, which we just used, and at the 05 level in a two-tailed test, Z, the critical boundary, the critical Z there, is positive and negative 1.96. It's also possible to test at any level of significance, but the most common are 5% and 1%. The Z-score that traps the middle 99% of values, well, folks, that's plus and minus 2.576. Okay? Two-tailed test means that you really are saying, I think that my result is different from what's predicted. I don't know if it's bigger or if it's smaller. I just think that maybe it's not the same as. It's also possible to hypothesis test in this kind of situation where you're looking at unusual values only being on one end. In that case, you'd be testing whether or not you think your test statistic is less than what they predict normally or what would normally be believed. At the 05 level, the Z-score that traps 95% of the values above is negative 1.645. At the 01 level, that Z-score would be negative 2.33. And those can be verified quickly using the Z-table. A right-tailed test, as you might imagine, goes the other direction. I think that my test statistic is showing larger than what they would normally predict. That would be testing at the right end of the spectrum or unusual values out here. The Z-scores are the same, or with a sign change, obviously. At this end, it would be a Z of 1.645 at the 05 level. Testing at the 01 level, the boundary there would be 2.33. And we'll see those numbers crop up the rest of the year. Okay? The 05 level, 01 level are the most common. In our work today and tomorrow, our hypothesis tests are all going to be two-tailed. That is, our alternate hypothesis will be that our p-hat is different from the population proportion, different from what they think happens. We want to talk a little bit about vocabulary, and then we'll move into an example. Our first example was an informal hypothesis test. I say informal because there is a procedure, okay? An informal hypothesis test. The criteria that we have to meet are the same as for a confidence interval, folks. We need it to be so that NP-hat and NQ-hat are both greater than or equal to 10. That's the size, the sample size criteria. The population criteria is that the population must be greater than 10N. And finally, we need to have binomial independent trials, random binomial trials. Binomial accounts for independent. So when you say binomial, then you're including the independence criteria. So the way that a formal hypothesis test goes is the commonly held belief is called the null hypothesis. The symbol for that, H sub O. Okay? In our test, our null hypothesis would have looked like this. H sub O is that P, the population proportion, is equal to 1/6, because 1/6 of the time you should have gotten sixes. You should write that in words as well. I don't think I have room to do that here, but this is the commonly held belief, what they think is true. The commonly held belief. The alternate hypothesis is what the statistician thinks might be true. Our textbook calls these H sub O and H sub A. And I've seen it called H sub O and H sub 1. However, our text uses A. The alternate hypothesis in our test was, well, I don't think that I got a population proportion of 1/6. I think I got something different than that. This is what you think may be true. Whoops, may be true. All right, the test statistic is exactly the thing that we just did, folks. It's the z-score for your p-hat sample. So z is equal to, and it's p-hat minus p, all over the standard error of the proportion, sampling distribution for the proportion, and that is, okay, now we're going to be careful because we're believing, the commonly held belief is what we want down here, p times q. Okay, you're not going to say that it's your sample. You're going to say p times q because that's what's supposed to be true, divided by sample size. For us, again, the values are on the calculator. The p-hat was 12/40, the commonly held belief 1/6, and then 1/6, 5/6, and 40 because we had 40 dice rolls. So it's just the z-score for a given p-hat. Okay. We did not test, we did not find the p-value in our informal test. I want to give you a definition for that, and we'll look at that in just a moment. But the p-value is the probability that another sample would have as extreme a result as yours did. That another sample would be more extreme, as extreme or more extreme than yours. You know, when you're talking about z-charts, that the equals to thing is really not possible. So that another sample would be more extreme than yours. Okay, and we'll show how to find that p-value in just a moment. The judgment that you make is based on, did your z fall in the critical region or beyond the critical value, if you want to think about it that way. You can also make your judgment based on the p-value. Is the p-value less than the level of significance? And the variable that they use for level of significance is alpha, so it's hard for me not to say, is the p-value less than alpha? Those are the two ways that you make your judgment. You state your conclusion in a rather odd way. Again, we're setting up a formal test here, and there is language that must be followed. The conclusion, if your z did not fall in the critical region, that is, I'm going to draw up here, sorry for going backwards, but in our test, our critical region was here and here. We had to get beyond negative 1.96 and 1.96. If you don't, if you find the z-score that does not fit in there, that is, your z comes in somewhere between those two, what you're saying is that your sample's not strong enough to overturn the null hypothesis. The language for that is a little bit stilted. What you conclude, that you fail to reject H sub O. That would be, again, if you don't fall in the critical region. What you're saying then is that your sample wasn't strong enough, didn't give you significant evidence of a change. You don't say that you accept H sub O, because as statisticians, we hedge our bets. You can't say that it's true because there could be some sample where it's not true. However, you say, based on my sample, I failed to reject H sub O, my sample wasn't strong enough. If, on the other hand, we do fall into the critical region, like we did with our test, because our statistic was way out here at 2.33 somewhere, if you do lie in the critical region, the language for that is reject H sub O. And again, you'd make some statement of conclusion, as we'll see in just a moment, based on the context of your test. So this is a formal test. It has to have these parts to it. First off, you must check criteria, especially those of you who are going to write the AP test, but you're all going to be taking a test for me, and I'm going to expect to see that you checked all three criteria. Stating the null and alternate hypotheses is the second step in that test. Computing the test statistic, that is finding the z-score. The judgment, I'm going to call the judgment the fourth element, and that includes finding a p-value and looking at a diagram of where your z falls. And finally, writing a conclusion for the test in terms of your context. Let's see how that plays out here. In 1999, an article reported that 2/3 of the teens in grades 7 to 12 wanted to have a career in the medical field in some form. You wonder if this still is true today. So you take a random sample of 40 teens. You find that only 23 of yours plan to work in the medical field, which is shy of the 2/3. We want to perform a formal hypothesis test at the O5 level. Our alpha, our level of significance, is going to be O5 to determine whether the proportion has changed. We're not saying whether it's less or whether it's more, just whether it has changed. So folks, our null hypothesis is going to be a not equals to, and we're going to be doing a two-tailed hypothesis test. The first step is to check criteria. The sample size criteria says that both NP and p-hat, and that would be 40 times 23 over 40. We want that to be bigger than 10. It obviously is. If that condition is true, then q-hat will also be true, the q-hat part, because it'll be the leftover from 40. So the sample size condition is checked, and really what we should write there is that n-p-hat and n-q-hat are both greater than 10, and they are 23 and 17. The next thing would be the population criteria, and the population of teens in the United States, or even in our school, is definitely greater than 400, 10 times 40, so that's okay. The last criteria is that you were binomial trials and randomly selected people. We are binomial. They either do want a career here or they don't, so we are binomial and random. Okay, those are the three criteria that we must check. The next step is to set out the hypothesis test itself, and we begin by stating the null hypothesis, that we believe the population proportion is 2/3. That's what the article said in 1999. 2/3 of 7th through 12th graders want a career in medicine. You can hear that back there, that's my washer. The alternate hypothesis is what we're going to say based on our sample. We think that P may not be 2/3. We think it's different than that. Okay? So we've got steps 1 and 2. The next step is to find the test statistic. So we need a z-score for our p-hat. Our p-hat was 23/40. We're going to subtract the 2/3 that they said we should expect. We're going to divide by the standard error, 2/3 times 1/3 divided by 40. Again, you're using P and Q down here, not the hats. The only place the hat appears is right there. I'm going to do mine, and I'm going to ask you to do yours, so I'll catch up with you in just a second. My z-score came back negative, less than we expected, but negative 1.23 approximately. So now I make my judgment. That's the fourth step. I'm testing at a level of significance of 5%, and the boundaries for a 5% test, negative 1.96 and 1.96. This is the critical area. So our statistic, negative 1.23, while it's less than the mean, is not in the critical region. We don't fall in the shady part, is what I often say. Well, we have our Z statistic. We realize that it's not falling into the critical region, but we also must check a p-value, it's called. And what we said earlier is that the p-value is the probability that some other test statistic would be as extreme or more extreme than yours. Well, in order for that to happen, folks, that means that somebody else's test statistic would have to come in here somewhere between negative 123 or 1.23 outside of that or outside of this. And if you think about that for a moment, we can check that, the probability that you would land either less than negative 1.23 or more than positive 1.23 by just looking at our z-table. And you can see that I have a little snippet of a z-table up here. I'm going to pull it into I just copied the part that I needed. Our test statistic was negative 1.23, and I have the negative 1.2. This is 2.0, 2.1, 2.2, 2.3. You'll see that the probability that you get less than negative 1.23 is that 0.1093. Well, knowing that the normal curve is symmetric, the same probability occurs at the top end. That is, to be higher than 1.23, that's a second of that same number. Let's add those together and we'll get a total value for our p-value here. 0.2186. Now, if you think about that, this is our p-value. It is the probability that we would be even more extreme. Another statistic would be more extreme than ours. And to check, to make your judgment, you do both things. Look at where your test statistic fell. We didn't hit the shady region. Look at the p-value. 0.2186 is not less, okay? So this is going to sound weird, but this is the way to think. It's not less than alpha. Our alpha was 0.05. Therefore, our conclusion is as follows. We fail to reject. We didn't hit the shady region. Our p-value is not less than alpha. H sub O at the 0.5 level. Now we must tie it to the context, the population proportion, and yeah, I'm going to say population. The population proportion of teens, or of 7th to 12th graders, who want a career in medicine, is not significantly different from 2/3. Okay, and we're going to call a halt right there. I'd just like to ask you to think about the logic of this again. Our test statistic was certainly different from 2/3. 23/40 is not the same as 2/3. However, it wasn't extremely different. And a hypothesis test, that is what you're looking for. Is it significantly different from what you would expect? I want to just take just one more moment. I want to underline keywords in this conclusion, because there are things that have to be there. There must be a statement of either fail to reject or reject H sub O. You should list the level. If it's not listed, it's assumed to be the 0.5 level, but it's safer to list it. What you're saying then is your sample was not significantly different from what they said. We failed to reject. There is no significant difference. You also must include a contextual link. Okay, there has to be a link back to the problem that you were solving. So tomorrow we will look at this more in depth. Get out there and try that U-Try, and we'll see you in class tomorrow.